next I want to discuss the mole. Moles are how we package chemicals. This comes from a guy named Avogadro, and if you've ever heard of this, Avogadro's number is 6.022 usually, but sometimes you can drop the last two, it depends on how many significant figures you want. But 6.022 times 10 to the 23rd is 1 mole. This is the number of hydrogen atoms that are in 1 gram of mass. So I want you to think about how big that really is. That is a huge number. If you counted for probably most of your life, you wouldn't hit that number. This is a lot of stuff. But that's how many atoms have to come together to make just 1 gram of hydrogen. That's a lot. On the periodic table, I can look at these values and see how that's 1. It's 1 with some digits out there. There's a reason why, and that's because of the fact that you have other types of neutrons that weigh in. But most hydrogen is going to just have a mass of 1 there. Okay. If you look on the periodic table, you can actually determine the mass of 1 mole for any element. So here's oxygen's 15.9994. Fluorine's 18.99. It depends on how many significant figures you want to go there. But that's how much 1 mole of that compound or of that element is going to weigh. Now, if you have 1 mole of water, that means that you have 6.022 times 10 to the 23rd atoms of oxygen and twice that amount, because this 2, atoms of hydrogen. So remember, this means H2. So 1 mole of water can give you individually 2 moles of hydrogen or 1 mole of oxygen. And that's a relationship that you can use. It's the difference between counting a sock and counting a pair of socks, because this comes sort of together, okay? So that could be its own conversion factor. For example, in CaCO3, that means for every 1 mole of Ca, there's 3 moles of oxygen. So we can use math all around this concept. Okay, so 1 mole of hydrogen atoms, if you look at the average, is all this amount, right? If 1 mole of H2O molecules is what you're trying to find the mass of, then what we do is we just add together 2 moles of hydrogen and 1 mole of oxygen, and that's how much a mole of water will weigh. So here we go. 2 times the mass of hydrogen, so 1 times the mass of oxygen. 2 times 1.00079 is where they get this number here from. And oxygen's 15.99994. Okay, so there's only 1 of those. So that means that 18.01, give or take some sig figs there, is about the mass of water, of 1 mole of water. We refer to this as the molar mass of a compound or formula. Sometimes we refer to MOLE as MOL. You'll see that very commonly. Okay. Molar mass is different for most compounds and can differ widely in values, the same way that, see how this guy's 208 grams for 1 mole of bismuth? That's an awfully large atom, but he is large in comparison to something like hydrogen. So that's how things can differ very widely. But just as with any other conversion factor, we can make an inequality. These two are equal. We could use this over this, or this over this in our math, because 1 mole of water is equal to that many grams, and this many grams is equal to that mole of water. Okay. So let's do some problems here. Okay. If a water bottle contains 10 grams of water, how many molecules of water are there? Well, we've got 10 grams of water, because that's what we have in the problem, and we just figured out that 1 mole of water is 18 plus grams. And we know by Avogadro's number that there's 6.022 times 10 to the 23rd molecules in a mole. So we just multiply that out. Be careful. Whenever you're using 6.022 times 10 to the 23rd, you might want to put parentheses around him if he's on the bottom ever, just to let you know. When he's on the top, it's not that big of a deal. So it would be 10 times this divided by your 18.0153, and that will give us 3.3 times 10 to the 23rd molecules. I suggest that you check your calculator just to make sure that you get that answer, because if not, you could have other issues going on with your particular calculator. I'm going to skip the next one and come back to it. Let's say, I'm going to go with the pink here. If you have 12 grams of Na2CO3, how many moles of oxygen do you have? Well, okay, whenever you have a gram and you need to go to moles, you've got to figure out the molar mass of this guy. Okay, so that's the first thing that I did. I figured out the molar mass. That's 105.99 grams per mole. So if I have 12 grams of that, I'm going to flip this value, which we could do because we did it on the last sheet. That many moles per grams. And then for every mole of Na2CO3, I've got 3 moles of oxygen. So that's going to give me the value here for 0.340 moles of oxygen. On the other hand, if we do this middle problem, if you have 12 grams of Na2CO3, how many atoms of oxygen do you have? This is a much different problem, but not really. Because in this case, all we need to do is say, we've got grams, we need atoms of oxygen. So instead of switching this, or stopping at moles like we did down here, we just need to figure out how many atoms there are. So 12 grams, 1 mole per the 105.99 grams, 3 moles of oxygen per mole, and then we just say, hey, there's Avogadro's number. So these numbers are huge, 2.05 times 10 to the 23rd atoms of oxygen. That's a lot of oxygen atoms. Atoms are huge in number in comparison to moles, and that's the way it should be. That's okay. Okay, thank you very much.